So I want to start today by reminding us of what the chain rule is and go through a couple examples to ultimately come to sort of a new way of looking at the chain rule. Well, new maybe is too strong a word, but just a way of looking at the chain rule that will make maybe quicker work of going through the process of taking derivatives by the chain rule. So the main idea behind the chain rule is that whenever you're trying to find the derivative of a given function, dy over dx, you could sort of do that in two bite-sized pieces. Could be convenient based on the situation. In particular, what dy over du times du over dx is dy over dx. So this is the idea behind the chain rule, and then let me go through these two examples to sort of remind ourselves of how this shows up. So if we have a function of the form cosine of x cubed plus 7x, the idea here is, man, it's unfortunate that inside our cosine function is another function. If our original function was just y equal cosine of a variable, that would be super simple to take the derivative of. However, you can get to the point of rewriting this cosine of a variable if you just take what's inside and express it as a variable. So take what's inside and let that be our variable u. And if you think now, these two statements combined form the original statement. The original statement was we have the function y equals cosine of x cubed plus 7. And if we let u be x cubed plus 7, then our function is y equals cosine u. And then, as we proceed to the chain rule, what we're looking to find is the derivative of our original function. We're looking to find dy over dx. And so in order to get things in terms of derivative, let's take the derivative of each of these two pieces. So the derivative of y equals cosine u, well, you know the derivative of cosine u is negative sine u. And in particular, the letters here that we're going to deal with, this is not a dy over dx because our variable here is u. This is our dy over du. This is that guy right here. Okay, and then let's take the derivative of this other guy. This is a statement of u in terms of x, so this derivative will be du over dx, and the derivative here is just 3x squared plus 7. And now, taking these two derivatives and multiplying them together, we know that dy over dx is just dy over du times du over dx. So in particular, what is dy over du? That is minus sine of u. And what is du over dx? That is 3x squared plus 7. But now we don't write this as our answer because the original problem only involved x and this involves u. U was sort of that substitution that we made that made things helpful. So let's get it back in the form just in terms of x. But you can do that because you know that u is equal to x cubed plus 7x. So if you just replace u with x squared plus 7x, we'll get sine of x cubed plus 7x times 3x squared plus 7. And here is our derivative. Okay, let's work this other example here, again, to see the action of taking the chain rule, and then once we do both of these examples, we'll be able to sort of take a step back and see a bigger picture point of view. So when you look at this function here, you have y equals this large thing in parentheses to the 10th power. And when you look at this, you might think, man, I wish this function didn't have this large expression inside of it. I wish that what's inside of it was just a u. Well, to make that the case, then you could just rewrite this function as y equals u to the 10th, which is super simple to take the derivative of, 10u to the 9th, no sweat. In order to write the original equation as such, we set u equal to that clunky thing that was inside the parentheses, so we set u equal to e to the x plus 5 ln x minus 7x squared. And now, if we want to find the derivative of our function, let's take the derivative of each of these component pieces to see what ultimately results. Here we have a function of y in terms of u, so when we take the derivative, this will be dy over du, 10u to the 9th, and here we've got du over dx equals, well, the derivative of e to the x is e to the x. The derivative of ln x is x to the minus 1, so we'll have 5x to the minus 1. And what over here, the derivative of minus 7x squared minus 14x. But the long story short is we have a dy over du and a du over dx, and we know that the derivative of interest dy over dx is just dy over du times du over dx. So sort of cobbling together these two expressions, dy over du was 10u to the 9th, du over dx was e to the x plus 5x to the minus 1 minus 14x. And now we don't exactly leave our derivative as such, even though dy over dx is equal to this. Our original expression only involved x. This u was just there to sort of help us along. So let's get the u back out of the expression. And so in other words, when we write our derivative, we'll have 10 e to the x plus 5 ln x minus 7x squared to the 9th. All we did here was replace u with what u was equal to. And then we multiply by that other factor that showed up, which was e to the x plus 5x to the minus 1 minus 14x. And this is now our derivative. Okay, and the goal really here, and really what this video is about, is now sort of looking at the process of what resulted when we started with each of the functions we did, and we ended with each of the derivatives that we did, and we say, is there sort of a way, maybe, that we could sort of view this chain rule process under a different light? And I claim there sort of is, because you see, if you take this original function y equals cosine u, and you just think of it as y equals cosine of something, then you can see that that cosine of something ultimately is what shows up at the beginning of our expression, because the first part of our derivative is negative sine of that same something. So that's interesting, because that first part of our derivative was just the derivative of cosine of that something if we leave the something inside alone. But then that's not the entire derivative. The entire derivative also involves this 3x squared plus 7. But what can we say here? We can say that this first part is the derivative of the outer function, leaving the inside function alone. And then this thing that popped up in the end, this 3x squared plus 7, was just the derivative of what's inside. So let me write this out in words. The first part of our expression was the derivative of the outside function, leaving the inside function alone. And then this last guy was the derivative of the inside function. But now let's look at that in context with the other example that we saw. Because when you look at this example and you sort of look at it for what it really is, it's really just a bunch of things raised to the 10th power. So if you first look at the outside function is just something raised to the 10th power, which you know how to take the derivative of that. Bring the power down, reduce the power by 1. And note, the first factor in our expression that results is just exactly that. It's taking the derivative of the outside function, leaving the inside function alone. The inside function did not change. That was our u going through the process. But what did change was that our outside function, the something to the 10th power, we brought the 10 down and reduced the 10 by 1. But now that's not the end of the story. That's only the first factor. What was the second factor that resulted? The second factor that resulted was the derivative of our inside function. And that is what came here on the other side. So the long story short is whenever we're doing the chain rule, this first factor is really, this dy over du, is really nothing more than taking the derivative of the outside function, leaving the inside function alone. And then the second factor is precisely taking the derivative of the inside function.